Hello and welcome to lecture 31. So today we're going to be talking about the net change theorem and indefinite integrals. Okay, we're going to start with indefinite integrals. So this is not a particularly deep thing. This is just a matter of notation. So we've learned that we can create a particular antiderivative from this function defined like this, what I call the increasing area function or the increasing signed area function. Yeah. Or is an antiderivative of little f, yeah, i.e. if f is continuous on this interval. This is fundamental theorem of calculus part 1. So in particular, getting an antiderivative somehow involves doing some integration, right? So we have this notation. We write f of x dx. Well, we don't put the limits in the integration. This is the indefinite integral, and this is, now this time I'm going to say the antiderivative because it's going to be the most general form of antiderivative where we put the function plus a constant. So this is the antiderivative of little f. So instead of writing capital F such that capital F prime is little f, we're going to write this to denote the antiderivative. So i.e. the indefinite integral of x squared equals x to the 3 over 3 plus constant c. Yeah? So, the key point. And this is a point that can cause some confusion. This is a function. Okay. And this is a number, which are completely different things, right? So these expressions look very similar to each other, but they mean completely different things, okay? And if you're in a hurry, you can easily get them confused. There's a high likelihood of there being a multiple choice question where you're invited to confuse the meaning of these things. Huh? Okay, so this right here, it's the indefinite integral, it's the antiderivative, it's a function, whereas if we do the integral from 0 to 1 of x squared dx, we know it's 1 over 3, that's a number. Cool. So with this notation, we can start to write down some antiderivatives. So I've already written down one. Let's do a couple of examples. So, example, if we look at this, what is this? What is the antiderivative of 1 over x squared? It's going to be minus 1 over x plus constant c, right? We differentiate this to get this. Let's do another example. Let's do sec squared. Yeah, what's the antiderivative of sec squared? It's going to be tan of x plus constant c. So if you look in the book, there's a whole list of antiderivatives, and they're written in the form like this. And when you have an exercise where you're given something like, well, let's just give you an example. So if you're given something like Okay. There are no limit signs here. It is asking you for the indefinite integral, in other words, the antiderivative of this expression. And we can just work it out, right? So we ask ourselves, what do we differentiate to get 10x to the 4? Well, the power has to be x to the 5, right, to differentiate to get down to x to the 4. If we differentiate x to the 5, we have 5x to the 4. It's not quite the right thing, so what we need is to multiply it by 2. So if we have 2x to the 5, and we differentiate that, then sure enough, we get 10x to the 4. So that guy is right. This sec squared we just talked about, so the minus 2 we just pull out. This thing is going to be tan of x, and then some constant c, and that's it, right? So if you see something like this, where it's an integral without the limit signs, it's an indefinite integral, it's asking you for what the antiderivative is. Yeah? As I said last time, now that we have the fundamental theorem of calculus, finding an antiderivative is extremely important because that's all we need to do to actually calculate these definite integrals, yeah? Which is another reason we have this kind of notation that essentially the hard work of calculating definite integrals comes down to finding antiderivatives. Okay, so that's all indefinite integrals are. It's just notation for the antiderivative, the most general form of the antiderivative. Okay, cool. So that's the first part. Now, let's talk about net change. So, from the fundamental theorem of calculus, so if capital F is the antiderivative of little f, then integral from a to b of little f dx, this definite integral is just given by this. Yeah, that's the statement of the fundamental theorem. So, since capital F is the antiderivative, then little f is just capital F prime. So this is the same as writing that the integral from a to b, capital F prime of t dt, is f of b minus f of a. In other words, if we use this thing, this generalized addition, which is the definite integral, to add together all of these rates of change over every t between a and b, then we get the net change in f. And I gave an example of this when we were first talking about the area integral, I think 2 videos back, which is to motivate why calculating the definite integral is actually an interesting or like more than interesting, it's an essential thing. And that was the example of considering the case when we have velocity being recorded, but no ability to measure distance except from velocity. So the thing I asked you to imagine was some future time when we are actually flying in space with rocket ships and directing them in some direction, right? And then all that we will know is what we input into the rocket, right? Which is we'll have control over the thrust, so we can increase or decrease the thrust, turn off and on the rockets to whatever extent, which will increase the acceleration, or decrease it if we want to fire rockets going in the backwards direction. So we will have control of the acceleration, which means we'll have control of the velocity because we will just get the velocity from the antiderivative of the acceleration. So millisecond by millisecond, we will know exactly what the velocity of our rocket ship is, right? And as we go off in a straight line with our rocket ship, we will be able to work out how far we're going by integrating up this velocity. And the net change in our position will be given by the integral of this velocity. Right? And if we think about this, that's the only way we'd be able to do it, because if we're out in space, there's no GPS, there's no nothing to make any reference to, right? So all you will be able to do to figure out how far you've gone is to very carefully record what your velocity is, millisecond by millisecond, and then integrate it. But that really will give you exactly how far you've gone because of this powerful theorem. So that is one of the most natural examples, and that is this example of linear motion. So let's put that down as an example. So practical examples. Not examples. Examples. Okay. If S of t is position, then S prime of t equals v of t is velocity, and net change in position otherwise known as displacement, will be given by the integration from a to b of the velocity. Okay, and by this theorem over here, since velocity is s prime, this is s of b minus s of a. In other words, wherever we are at b minus wherever we are at a, that's the displacement, that's how far we've gone, right? Cool. And as we're going to see later, that's not the same thing as total distance traveled, but we'll get to that shortly. Let's first just talk about some more examples of this. So let's see if I can squeeze in next example. So let's do the next example in here, if we can. So let's call this example 1. So it's example 2. So this is an example of water going into a reservoir. I don't know how to spell the word reservoir, so I'm going to call it a lake. So supposing we have some lake that we are using to to provide water to a community, a lake, which is basically a reservoir, right? So we have this chunk of water, this big mass of water, and we let some of it out according to need, right? So sometimes there's greater need, it's summer or whatever time people turn on their sprinklers. Sometimes there's less need. And we also have water going in. Maybe we are having it coming in from some dam, whatever, maybe it's being pumped in, whatever. We know water, we can control how much water is going out, and we can control how much water is going in. Yeah, and suppose we can also know the rainfall dropping water from the sky into our reservoir. Yeah? So let V of t denote volume of water in the lake, because for spelling purposes we're calling a reservoir a lake. So this is the volume of the water in the lake. Yeah? And as I've just described, we will know what the rate of change of that quantity is, because we control how much flows out, we control how much flows in, we record how much drops in from the sky. So we know what V prime of t is, right? And supposing there's some moment in time when you turn on all these sources of water and you don't let any out, so you fill the reservoir up to as much as you possibly can, so you know its total amount because you filled it up. Huh? And then you're managing the reservoir and the water's going in and out, and say at a certain point you want to know how much you've got actually left in your reservoir, because maybe it's just turned to spring and the weather forecast is that we have a long hot summer, and you want to know if there's actually enough water in the reservoir to fill the needs of the community that it's serving. Then what are you going to do? Well, it's a very hard job to actually try and estimate that, because the reservoir could be like whatever weird shape, and maybe one time there was some guys with some X-ray technology to find out the total volume, but if the water is at this level, then that's a much harder job, to find out how much water there is when there is this amount. But you can use the information that you do have, which is this v prime of t, yeah? Because by the net change theorem, we know that v of b minus v of a is the integral from a to b of v prime of t dt. Yeah? So we can explicitly calculate it. We just use this definite integral using the data we have, and we can find out exactly how much water we have, right? So if at a, time a is when we knew how much it was, we filled it up to whatever, right? Then at time b, the start of summer, we know how much there's going to be left by calculating the definite integral of v prime. And that, again, is of real practical use. And yeah, that would make life a lot harder. And if you didn't do that, what would you be doing? Then you would be calling out the guys with the radar technology to try and estimate what the volume of this stuff is. But if you just have a bit of math, then you can actually, and you've recorded the data of how much you've let flow out compared to how much you've let flow in, then you don't have to do that. Then you can figure out as precisely as you want how much water there is left in the reservoir, and the only error will be just in the error of how good you've made your data collection, how good you've recorded how much is flowing in, how much is flowing out. Huh? So another example of real practical use. And this is not an invented example. All right, I'm going to raise the board and then we'll talk about some more examples. Okay, the next example. So, example 3. Suppose we have a rod which is made up of a mixture of material. I should say a composite rod with variable density. So you actually do want to create things with variable density. So I ride bicycles a lot, and if you buy a very high-end bicycle, a carbon fiber bicycle, then the composition of the carbon fiber is different at different parts of the bicycle because the main aim is to make it as light as possible. So you want it to be of a stronger density or a thicker density at certain places where it has to accept a fair amount of stress, and then you want it to be lighter at other places where it doesn't. So you actually can manufacture things with variable density, and this has been true for a long time. So material scientists have a concept to try and understand this, and that's what they call the linear density. Yeah? So let m of x denote the mass of the rod up to x. Up to x, yeah? So if this is the start and this point here is x, then m of x is the mass up to this part right here. Yeah? So it's the mass of this part of the rod. Yeah? So let's blow that picture up. So if we want to try and understand what it means to have density at some particular x along the rod, what are we going to do? So the linear density rho of x is defined to be equal to the derivative of m of x. And then I'll show you why that's reasonable. That's reasonable for the following reason. So let's draw a picture like this. So this is the little section of the rod, say between x and x plus h. right? So if we want to get some idea what the density of the rod is, what are we going to do? Well, if we just look at the mass of that little piece, the mass of that little piece is going to be given by m of x plus h minus m of x, right? It's the mass all the way up to x plus h minus the mass before. That's the mass of that little piece. Yeah? But that thing is not going to tell us the density of that part of the rod on that little piece, right? If we do this, that thing will give us some kind of something like the average density over this little section. Yeah? Yeah? Because that's the mass divided by how long it is. So that's something like the average density on that little piece of the rod. And just in the same way we define derivative, if we want to understand the actual density at some particular point, we want to let h go down to 0. Yeah? So limit as h goes to 0, m of x plus h minus m of x over h is the actual density at that particular x. Yeah, and a little bit like velocity, the density at that particular x is the density of something that doesn't exist, right? There's no rod of thickness 0. Yeah, but nevertheless, it is meaningful and it is the right concept. If you want to understand the density at each individual part of the rod, then it has to be this limit of this quotient, right? Yeah, so it's actually really analogous to the concept of velocity, but it's less familiar. So think about this for a little bit. You'll start to believe that this is a reasonable concept. Yeah? So imagine we have a manufacturing process, and I'm certain these things exist, where we're manufacturing a rod, okay? And we can program in the density that we want, right? So we program in some function depending on how far along it goes. So at the beginning, perhaps it is small density, and then it gets denser as we want the rod to be stronger at some particular part. Yeah? So we can have this rod being outputted from our manufacturing process. Yeah? And perhaps we want to know what the weight of this rod is, or some part of this rod, yeah? Or what the mass is. Yeah? Then, by the net change theorem, and the net change theorem is just a fundamental theorem with a different name, right? Then the mass of the part of the rod between A and B, which is mass at B minus mass at A, is equal to the integral from A to B of this linear density x dx. And that's exactly what it is, because the linear density is m prime. Yeah? And if you're manufacturing a bicycle, then you really do want to try and minimize the mass. As I said, that's the main thing you pay for when you buy a $4,000 carbon fiber bike. You pay for something which is a couple pounds lighter than whatever, a $2,000 carbon fiber bike. And even more realistically, if you're designing such a bike, then because of this theorem, you can figure out how much various parts of the components of the bike will weigh based on what density you want to make them. And then you can do some other calculations to try and figure out what density you need them to be in order for the bike not to fall apart when you ride it, whatever, across a bumpy road. Yeah? So being able to precisely calculate what the mass of some piece of the rod is just from this density is a very good thing to be able to do, a thing of real practical value. Yeah? Cool. All right, perhaps one more example. I mean, there are many examples, but we have a finite amount of time. So, next example is population. So, let n of t be the population of whatever, let's say people at time t, okay? If we know the rate of change of population, then by the net change theorem we can find the total change in population, or the net change in population. Let's use the same notation. Okay. And again, this is of real value. So in the US, I think you have a census every 10 years, trying to count the number of people there are all around the country, and in every county, in every city, in every state. And these are of enormous importance. So if you have a good estimate of how many people there are in various places, then you know how many political representatives you have the right to have for that region. You know how much federal spending you want to put in that region to support various things, various services. You know how much disaster relief to allot to that region if something goes very wrong. It's a very important thing to know, but it's also a very difficult thing to know precisely, because it's hard to count people, right? It's a big effort. It's a lot of investment to go around and count everybody wherever they are. So that only happens once every 10 years. But you do know a lot about the population change in some region, because you know how many people are dying. Every time someone dies, then there's a death certificate. There's an administrative record. Every time someone is born, there is an administrative record. When people get their driving license and they reach adulthood, you get an administrative record. You have a record of the number of people reaching voting age, the number of people dying. You also have a record of how many people enter some particular state. They get a new driver's license for that state, and a record of how many people leave. They get a driver's license for another state. They leave. They're no longer there. So you do have a good way to record the rate of change of population. Yeah? And with this information, by integrating this, you can have a very good estimate what your population of whatever thing you're counting, city, county, state, is from that information. Yeah? And that is how these estimates are made. And it's not something you can do without fundamental theorem of calculus. It's not a constant quantity, right? The rate of change will be variable. So the only way that this is true is if you actually integrate this with a definite integral, just in exactly the same way if we want to record the total displacement of something with variable velocity, then there's no other way to do it except with the integral, right? We can't just multiply the time by some constant quantity, because it's not a constant quantity. Yeah? And some of you might be thinking about this a little bit and thinking, well, surely this is nonsense, because we're doing calculus, we're talking about functions that are differentiable, and this thing here is not anything like a continuous function, because we only have information for every day. So we just have this block. We have this thing that's defined on just little isolated intervals, right? And I agree, that's a smart observation, but let's take a look. So if we have, we do have daily information about this, how many people die every day, how many people apply for and get their driver's license in the new state, whatever. So reasonable to say that this is daily updated. Yeah? And if we think about how many days there are in 10 years, that's like 3,600 something days, right? So we have these 3,600 little pieces of information, right, about what is this thing. Yeah. So we can plot these points like this. Yeah. Because we have these data for these individual days and just connect it up. And then with this thing, we can apply the fundamental theorem of calculus and get this actual data here. Yeah, get this total change, this net change in population for whatever we're thinking about. So this is, again, of real practical use. Yeah? And in this case, I think there's nothing else you can do, right? Short of carrying out the census many more times than once every 10 years, if you want to have good data as to your population, you are forced to use the fundamental theorem of calculus. There is no other thing. Yeah? There's no other thing. And I don't know if municipalities are actually doing this. I hope they actually are. But But yeah, that would be the way to do it. And the better data that you have, the more you can make a good case for whatever you want, for state funds, for federal funds, for political representatives. So another definite benefit of calculus. All right, or at least of this particular net change theorem. So as you study more things, if you study things in economics, if you study things in engineering or any of the sciences, there are more and more quantitative examples where figuring out the net change from being able to integrate this rate of change becomes a thing of real value, a thing of real practical value. As you think about this theorem more and more and get more and more comfortable with it, it will seem more and more natural to you. We have this very sophisticated way of adding over this infinite set of points between A and B, and we add this infinitesimal rate of change, and that thing gives us the total change. So these kind of ideas of like the yin and yang. So the rate of change is something which is recording change in an infinitesimal scale. The integral is adding up this uncountable infinity of infinitely small quantities, and we can put them together magically to find the total net change. So this is one of the once you feel familiar with calculus, then this is kind of one of the facts which is somehow in the essence of calculus. The essence of calculus are these two main ideas: the derivative and the integral, and they combine in this very beautiful way here to give us the fundamental theorem. Now, as I said on the last lecture, this is one of the absolute intellectual high points of your entire degree, of your life probably, certainly of my life. So please invest some time to think about this and appreciate its power. All right, so that is our examples, but let's go back a little bit and talk about the first example, which was the displacement coming from integrating the velocity. So imagine the following. So suppose the velocity is given by v of t, okay, which has a graph which, say, looks like this. Okay, so this is A here, this is B, this is C, and this here is D. Okay, let's think about what happens as I go along with velocity given by this graph. Well, as I start off, suppose right here at the edge of this board is where I am at time A. Yeah? So as I go forward, or as time starts to run forward, then my velocity is positive, but it is decreasing. So I'm going forward, but I'm slowing down, and finally at B, I stop. And then at B, I start to go backwards in velocity, right? I have negative velocity. So I stopped, I start going backwards, I go backwards faster and faster and faster. My maximum velocity is somewhere here between B and C, or my maximum negative velocity, yeah? And then I'm slowing down, and when I reach time C, I've stopped, yeah? Okay, and now I'm changing velocity sign again, and now going from negative velocity to positive velocity. So I'm going forward from 0, faster and faster and faster, until here I am at D, yeah? So what did I do? I started out at A, I went forward to time B, and then I stopped, and then I went backwards, B to C, then I stopped, and I went forwards again. And here I am at time D. Yeah? So my net displacement is where I start to where I ended, which was like around here. Yeah? But that's not the total distance I traveled, because in the middle of that journey, I stopped, went backwards for a bit, and then went forwards for a bit. Yeah? I did something like this. I went forwards, then I went backwards, then I went forwards again. Yep. So this is where I was at A, and this is where I was at D. Yeah. But the total distance I traveled is this plus this plus this. Yeah. So total distance is not the displacement. So let's write that down as a fact. So total distance traveled is not displacement. Yeah. So if we want to figure out the displacement, then we're going to have to, if we want to figure out the total distance traveled, we're going to have to add the length of this part of the journey plus the length of this part of the journey plus the length of this part of the journey. Yeah. So we can't anymore just integrate the velocity, because we know that'll just give us where we are at B minus where we are at A. Yeah. Where we are at D minus where we are at A. Yeah. That's right, this is D. That's right, S of D, S for the position. And this is S of A. Okay, so we have to come up with an expression that will give us the total distance traveled. Yeah? And for this part, which is between A and B, right, if we just integrate between A and B, the velocity, then we're just going forward, and the total displacement from A to B actually is the total distance traveled from A to B. Yeah? Now when we do from B to C, we're going backwards. Yeah? So the total distance traveled won't be the displacement, because the displacement's negative, but it will be the absolute value of the displacement. Yeah? So the total distance traveled will be this length, which will be minus the displacement, because the displacement is where we are at B minus where we are at A, where we are at C minus where we are at B, right, which is a negative quantity. So let's write that in. This is, right here, this is S of B, and this is S of C, right here. Yeah? So, to actually have the length of this thing, it's going to not be the integral velocity, right? It will be the absolute value of the integral velocity. Yeah? Because the integral velocity, again, will give us this negative quantity, how far backwards we've gone. Yeah? And the integral, or the amount we travel in this final part of the journey from S of C to S of D, this is just going to be the integral of the velocity, because now, again, velocity is positive. So, what we've learned is that total distance traveled is the integral from A to B V of t dt. Yeah, that's the first part, and we know that we have to have negative of the next part, or the absolute value of the next part, right? The absolute value of B to C V of t. Yeah, and then the integral from C to D. Yeah. Now, since our velocity here is negative, right, from B to C, taking the absolute value of this will be the same thing as multiplying this just by -1, which you can take inside this guy here, right? Let's write that over here. So the absolute value of B to C of V of t dt, since the velocity is negative throughout this entire time from B to C, right? This is just minus the integral from B to C of t, because it's just minus how far back we go. Yeah, which can put this thing right inside this thing. And that's the same as the integral from B to C of the absolute value of V of t, because V is negative in this part, so it's the absolute value. Yeah, and from A to B, V of t is positive, so V of t is the same as the absolute value of V of t, and from C to D, v of t again is positive, right? So putting that stuff together, so total distance traveled is a to d, and then it's the absolute value of v of t dt, right? Because we're just taking the absolute value of this part plus this thing, which we know is just the absolute value of this plus this, right? So if I break this up for you, it's equal to this. So I'm not changing anything by putting absolute value of around v of t here. We've learned that this thing is this thing, so it's this. And the final guy is this guy. Again, v of t is positive, so yeah. And then that stuff, all that stuff here, let's call this thing star. So star is just equal to the integral from a to b v of t dt. Yeah, so we actually do have this expression that gives the total distance traveled, but it's no longer integrating the velocity, it's integrating the velocity or the absolute value of the velocity. Yeah? Cool. All right, so with this, we're going to be able to calculate absolute value. We're going to be able to calculate the total distance traveled. I'm going to raise the board, and we'll do an example of that. So this is our example. A particle moves with velocity v of t is equal to t squared minus t minus 6, okay? And then part A. What is the total displacement from 1 to 4? And then part B, what is the total distance traveled? Okay, so solution. Part A. So, first part is just applying the net change theorem, just as we've discussed. We know the velocity, it's given by this, t squared minus t minus 6 dt. This is a definite integral. This thing we know the antiderivative of. So we write 4, 1. Then we put the antiderivative. We're going to have t to the 3 over 3 minus t squared over 2 minus 6t. Remember, we can use any antiderivative in the fundamental theorem of calculus. If we put a constant c here, it wouldn't make any difference because it would cancel out when we do the application at 4 and then at 1. So we just take the simplest antiderivative. We don't bother writing the c in this case. Huh? Then we just put the numbers in. So it's going to be 4 to the 3 over 3 minus 4 squared over 2 minus 6 times 4, which is what, 24. This thing minus what happens when we put 1 inside this. We have 1 over 3 minus 1 over 2 minus 6. And then just figure out what that is. And that turns out to be, I think, minus 9 over, I'm sure it is, it's minus 9 over 2. Yeah. So that is part A, no problem. Okay, part B, we have to think more. So first thing to notice, our total displacement is negative, so we end up backwards from where we start. So if we start here, this is S of 1, then S of 4 is right back here, right? Yeah, so we're going backwards like this. And the length we're going backwards is 9 over 2. Yeah? Because S of 4 minus S of 1 is minus 9 over 4. Yeah? So let me just emphasize this is S of 4 minus S of 1. Okay, cool. So obviously the total distance traveled is not going to be a negative number, right? And it's clear from this thing that we have negative velocity over our time interval from 1 to 4. Yeah? So look at our velocity function. It's given by this. Let's draw some kind of a picture. So our velocity function is some kind of a quadratic, like this, right? It's quadratic, which is going up. Yeah, this is v of t. And what we'd like to do is, I mean, it's clearly going to have negative velocity, so it's definitely crossing the x-axis somewhere. And what I'd like to do is to find out where it's crossing the x-axis, because if we find out where it's crossing the x-axis, then we'll know something about what is happening over the time interval 1 to 4, right? It could be that 1 is over here and 4 is over here, so we start out positive. So let's write that. It could be that 1 is here and then 4 is here. And if so, we start out positive, then we have negative velocity, then we have positive velocity again. That's a possibility, yeah? Or maybe 4 is here, and then we are positive, and then we are negative, yeah? So to find out what our journey is like with this velocity, we need to know when it actually goes from positive to negative and then back again. But it's just a quadratic, so we can solve it, right? So we find the roots of quadratic. Of t squared minus t minus 6. We're going to factor it, and the factors will be t minus 3, I guess, and then t plus 2. Yeah? So therefore, the roots are here at 3 and here at minus 2. And so I guess 0 is around here. And then our journey is this, right? We are starting out here at 1, and we're ending up here at 4. Yeah? Cool. So we therefore know that from time interval 1 to 3, we're going to have negative velocity. We're initially going backwards. And then from 3 to 4, we have positive velocity. Yeah? So to actually find this total distance traveled, we are going to need to have negative the quantity, which is the integral from 1 to 3 of this velocity. Yeah? Because that'll be the integral of the absolute value of the velocity. It will also be how far back we've gone, multiplied by a minus sign, telling us exactly the length of that backwards part of the journey. Yeah? So total distance traveled will be given by minus the integral from 1 up to 3 of this velocity function given by this thing. T squared minus t minus 6. And that's the same as just putting a minus inside here, and that's the same as having the absolute value of this velocity function because we know it's negative over this region. Yeah? So let's actually do that. That's integral from 1 up to 3 of v of t dt, which is equal to this. If you want, I'll put the minus inside so it looks more like the expression we have, minus like this, dt, and then the integral from 3 to 4 is now just going to be just the velocity function because it's positive on this part, so it's just t squared minus t minus 6 dt. Then we can just do the calculation. So then Okay, 1 to 3. And then what do we have? We have minus t to the 3 over 3. For this guy, we're going to have plus t squared over 2, and then plus 6t, and that's this thing. Yeah? And then, so it's positive, positive, negative, this guy right here. So then it's going to be 4 to 3, and then we have t to the 3 over 3, minus t squared over 2, minus 6t. Okay? And then what is this? Put the numbers in. And this turns out to be 61 over 6, which is 10.17. Okay, so we are happy because firstly, this is a positive quantity, so that at least is the right sign, because if it's length, then it's got to be a positive quantity. We also would expect that this quantity will be bigger than the absolute value of the displacement, which of course it is. It can be equal to the absolute value of the displacement if the velocity doesn't change sign. Yeah? If the velocity is always positive, then it will actually just be equal to the displacement. If the velocity is always negative, then it'll just be the absolute value of the displacement. Yeah? So this makes sense to us both in terms of its sign and its magnitude, which means its absolute value. And this is the right answer. So the actual calculation was just this and this. It's just finding an antiderivative of a polynomial, putting numbers in. It's an easy calculation. But to actually unwrap what you need to do from this information, you have to think about what is going on. You have to have a picture, right? You have to understand what this question is asking. Yeah, this is not something. This is not something you will have much. You could easily be tripped up if you're trying to learn this subject by memorizing algorithms. But if you are visualizing what this stuff is asking, what this thing means, this is not a hard question. You will come to this conclusion that you need to find out the part of the journey where the particle is moving backwards, and then the part where it's moving forward, and then you're well on the way. Another thing to say is that this is a good candidate for a free response question because it involves you having to think through something like this and present your thoughts and work through, which is the main thing we need free response questions for, right? So free response questions, as you know, are worth more points. It's worth, whenever you see something that you recognize will be a thing that is multiple stages, that involves some kind of interpretation of some situation using the language of math and then solving it. Good candidate for a free response question. Good to be particularly good at this. Okay, so I want to do one final thing because I was asked about this as an office hour, and I can imagine this could be tricky for lots of people. So we've learned about the fundamental theorem of calculus, part 1, and I talked about how the only reasonable way we have to test it is to create this function where we can only find the derivative by using the increasing area function and composing it with something else. And here's a kind of a slightly trickier manifestation of this. So this is the odd-ordered exercise 69. As I've said lots of times, please do the odd-ordered exercises as active practice on anything that you are not feeling too comfortable with. Practice these things, do whatever, do 5 questions, do 10 questions, do as many until you feel confident about this, until you see that you're getting the answers consistently right. Yeah? If you do that, then you will do well. If you get in the habit of just practicing this stuff, doing enough questions so that you can actually consistently get it right, then you will clean up in the exam. This is just a function of how much you practice. All right, so this is our example. And the way they're making this harder for us is that they have this stuff, the function of x both in the top and bottom limit, instead of just having it from whatever 1 or 2 or something. But we think about what this means. What does this mean? This is the integral from 0 to or it's the integral from 2x up to 3x. So it's integral over this thing right here. Yeah? And that's the same as the integral from 0 to 3x minus the integral from 0 to 2x, right? As we can see. So this thing, g of x, I should say what the question is, so find g prime of x. So g of x is, let me put it down a little bit, g of x is the integral from 0 to 3x of u squared minus 1 over u squared plus 1 du minus the integral from 0 to 2x of this 2x, 2 pi, of u squared minus 1 over u squared plus 1 du, right? Just this picture. We just see it, right? This thing is the same as this thing. Yeah? And then let's define this function h of x to be the integral from 0 to x of u squared minus 1 over u squared plus 1 du. Yeah? And then what? Well, then this thing is nothing other than h of 3x minus h of 2x. And then we're in a good position because we can just differentiate through. Huh? So g prime of x is equal to, just applying the chain rule, h prime of 3x times 3 minus h prime of 2x times 2. And we know the derivative of h because it is just the application of Fundamental Theorem of Calculus Part 1. And h prime of x is just equal to x squared minus 1 over x squared plus 1. Right? That is what we know. Yeah? Look back if you're unfamiliar with this. Hopefully at this point you're very happy with derivative of expressions like this. So we can just put in what this stuff is. So h prime of 3, we know what h prime is. So h prime of 3x, I should have said, is 3x squared minus 1. Everything is times by 3 over 3x squared plus 1. Yeah? And then minus, put this 2x inside this, 2x squared minus 1 over 2x squared plus 1, and then we're multiplying it by 2. So let's put the 2 in here. Brackets like this. And that is it. So it's not actually particularly hard. This is the only step you need to recognize that you can break this into this. And this you should see when you think about what the integral from 2x to 3x is, and recognize it's just the integral from 0 to 3x minus the integral from 0 to 2x. So, again, this is one of the few formulations where we can test the Fundamental Theorem of Calculus Part 1, so make sure you can do these kind of questions. But once you've done a handful of them, you should see that they're pretty easy. They go the same way every time. You create your increasing area function like this. You define the thing you're trying to differentiate in terms of the increasing area function composed with some other function, which is defining the limits, and then you just use the chain rule. Okay, that's it for today. I hope you had a great day. I will see the Friday group on Friday.